Okay, so yeah, I feel dumb. I didn't know what inertial forces were, and I thought these are conservative forces that we're talking about. But no, turns out inertial forces are just pseudo forces. So what I've been calling as pseudo forces all of this time, which are in fact pseudo forces. So these are also called inertial forces because they arise from the inertia of the body, right? Yeah. Uh, so we'll do 114 because the B part I didn't do it, right? So now I'm going to do it. Let's do it. So what is it saying? It says a horizontal disk of radius capital R rotates with constant angular velocity omega over a stationary vertical axis, passing through its edge. So maybe over here. Okay. Along the circumference of the disk, a particle of mass m moves with a velocity. So first of all, since we just want the inertial forces, let's just write down the formula for inertial forces for planar motion that we discovered, right? That I grabbed, and then just so the pseudo acceleration, right? So something that we have to add while going from the inertial frame to the rotating frame, right? Which so that is just what was it, like negative acceleration of the origin and then r naught hat. Sorry, it's supposed to be just r naught hat. It's like, yeah, like acceleration of origin that times r naught hat. So actually it should be like that. So yeah, e power -5 or something, you know. So e power -I5, where phi was the angle that this rotating frame's origin made with the axis of the non-rotating frame, right? So that was one thing. Yes, and a naught vector is the acceleration um, as seen in the non-rotating frame. So it's the acceleration of the origin of the rotating frame as seen in the non-rotating frame. And then when you rotate it clockwise by phi, what does that actually do? Yeah, it's just shifting everything back basically. That probably makes sense. So yeah, I mean, um, the thing is that this acceleration, it has like multiple components and whatnot. So you can just say it's a naught times r hat. R naught hat. That's not actually correct. So that I did in the derivation. And over here, so over there we were using complex numbers, so it was all justified because a naught vector would pretty much just be a complex number. Yes, and that's why it was okay. But over here, this is not okay. Okay. But the fact is that if we take, let's say, this as the origin, right? Then the angle that it makes with this thing. So if say after some time this became like that, so this is how it became, right? Phi, here's that origin. The acceleration on this thing, because it's rotating with constant angular velocity omega about this. So this is just going to be over here. Let's just use omega naught for now, and later on I'll put in omega, okay, in the final answer. So this acceleration also is always in this direction. So that's the acceleration of this point as seen by this, and then this times e power -I5, that is clockwise by phi. Just rotate clockwise, you get this thing as a thing, and then negative of that. So in this direction, it just, well, omega naught squared capital R. This thing is capital R, right? That's why that. Now, if there was some other component, you would rotate that as well and figure out what that should be in. Yeah, and this vector is this will be used directly in the what do we call it? Yeah, in the rotating reference frames. Okay. Yes. So it really is just omega naught square r along the x-axis in the rotating frame. So not in the non-rotating frame, but in the rotating frame, this has to be like that. Okay. Yes, this a naught vector is it directly carries on from what it was in the non-rotating frame, and then you just multiply by e bar I5, right? And after doing that operation, whatever the vector you get, you're gonna use that vector directly in the non-rotating frame. That's how we did it in that derivation. Okay. Yes. So in this particular case, it's just going along the real axis. So it's gonna be omega naught squared r. Okay. And other terms. So other terms included plus. So it had that r hat and t hat, and r hat was just e power I theta basically. Yeah. So the theta is, well, what angle the particle makes with the x-axis of the rotating frame, right? So this angle will be theta. Yeah, and that was just e power I theta times but r. Okay, yeah, it's supposed to be r over there as well. So small r is just the distance that, yeah, like the distance of this particle from the origin of the non-rotating frame. Sorry, rotating frame. Yes, and then this would be omega dash omega naught plus omega naught squared. Yes, and then you had a negative. All right, so negative I e power I theta. That's a tangential vector. Yeah, so basically this vector as seen in the rotating frame. Yes, and this had first the Coriolis force, so it was just 2 omega naught r dot, and then you also had that thing r alpha. So in this case r alpha naught. Yes, that was the thing. Now for this particular example, our alpha naught is 0, right? And our r dot is 0 as well, because that particle is rotating on the circumference, right? Along the circumference of the disk, a particle of mass small m moves with the velocity and is constant related to this. So in fact, your omega dash, that is constant. Yeah. So putting that in, this complete term is just gone. Oof, nice. You just get this thing. And what they are saying is, this capital R should just be, so this small r should just be capital R. Yes. And then they're saying that at the moment when the particle is at the maximum distance from the rotation axis, that is when the thing is, like, this is okay, just look at it in the rotating frame, right? So then the particle is just going like that. So then whenever it's furthest away from this axis, that will be this point, right? So that's the positive real axis. So its e power I theta is just 1, and that means omega naught squared r plus r omega dash omega naught plus omega naught squared. Oh, it should be 2. Sorry, it should be 2 over there. Sorry, I forgot that completely. That's what we're looking for. That is our inertial acceleration. Weird, right? Inertial. Fine. That's the thing. Now they're saying at that moment F inertial is 0, right? And that just means, okay, this quantity is 0. So that means 2 omega naught square plus 2 omega dash omega naught is equal to 0. R got cancelled anyway. And from here you can just say omega dash is just negative omega naught. This is the important thing from this condition. And now once we have that, they ask us to find the dependence of the inertial force on the distance from the rotation axis. So inertial force is just this complete thing and that times mass, right? But first of all, let's put it in here and see what we get. And in fact, we'll just put both omega. So I just put omega naught as omega now, and then omega dash just becomes negative omega. So then this will just become, well, omega squared r plus r e power I theta. So the radial vector, yeah. And then you got 2 omega dash omega naught, which will be negative 2 omega squared, and then this is just omega squared. So it's supposed to be negative omega squared. Cool. So it's just omega squared r into 1 minus e power I theta. Yes, that's what this thing is. So what does this mean? What is 1 minus e power I theta? What does it mean? So 1 is this, and then e power I theta is okay, let's just go to this frame. So the rotating frame, 1 is this point, and then e power I theta is just this point. So when you say 1 minus that, it is referring to this thing. But you could also think of it like slightly differently. You could think of it as like negative omega squared r, and then you got e power I theta minus 1. Now, what does this mean? E power I theta is just this thing. And then minus 1 is... Oh, okay, I think that's not how it should be. I mean, it's always going through that. Uh, oh god, that's not good. This is not good. Oh, okay. So we want a dependence of what? The inertial force on the distance from the rotation axis. Rotation axis is this thing. So actually you should look for e power I theta plus 1, but that's not here. Uh-oh. That wasn't supposed to happen. But it really is just negative e power I theta. So now what do we do with it? I really thought it's gonna be e power I theta plus 1 somehow, but no, that's not correct. Yeah, well, that's bad. Huh. So it really is just this minus that. This vector, that's the length that we're talking about. But how do I figure out what that means? Oh, this is 90 degrees, sorry. We can actually do this thing. So this is 90 degree. Call this thing as x. This whole thing is just 2r. Then this thing is just square root of 4r squared minus x squared, right? This length? Yes, yes. And look at that. This guy is just that vector. Yeah, it's just perpendicular to this, this vector, yes. And it has magnitude of this thing. So your inertial force has added up is just negative omega squared r square root of, well, 4r squared minus x squared, where x is the distance from this rotating axis, the actual original rotating axis. Yes, and its direction is just like here. Now how do I do that? Wait, you just want distance, right? So this should be enough. In fact, you don't want the direction or anything, you just want f in. Okay, this is not even in bold, so probably it just means it is a magnitude that we're looking for. So magnitude wise, it's just this quantity, omega squared r squared of 4 r squared minus x squared. So 114d, now we can do it. What was the thing? This omega squared r squared root of 4r squared minus x squared. Okay, finally you got it. Just delete all of this. And there was once again another question that used inertial forces. Where is it? Right, so 116. A train of mass, something moves in the latitude this. Okay, find the direction of the lateral force, yes, and in what direction, with what velocity the train should move for the resultant of the inertial force acting on the train in the reference frame fixed to earth to be equal to 0. So this is a train moving with some mass latitude given. Yeah. Magnitude direction of the lateral forces. Hey, so 116, we actually found a formula for that, right? Where did it go? Yes, so the force vector, I mean the pseudo force vector, sorry. Yeah, that was this thing, and then there was also like the Euler forces and everything, right? Okay, no, that's not here because alpha naught for Earth is 0, so that's gone. And then there's a centrifugal force, which is, that still is here. So yeah, there's a centrifugal force. There is this Coriolis force. Yeah, it should make sense. Equal to 45 km per hour. Okay, in what direction and what velocity should the train move for the resultant of the inertial forces acting on the train in the reference frame fixed to Earth to be equal to 0? Okay, this is just really bad. I think the vector cross product definition of this thing might be better. Or should we just go with the normal thing? No. Let's not go with the normal thing. Let's go with the vector definition. So there's that. Oh, come on. This is going to be so long. First of all, there's centrifugal force. Centrifugal force is just omega naught squared r, usually. Yes. But here it's going to be omega naught. I mean, okay, you can just go with it actually. Omega naught squared small r. So small r is just distance from the axis. Okay, which we can figure out. No problem. Sorry. Yeah, you got a centrifugal force which is acting outwards. Okay. Well then, what else do you have? Wait. Inertial force that you want to plane is 0, right? Okay. So its north velocity must be 0 because there's only one tangential force. Yeah, there's only one tangential force that this whole guy, I mean, like gets. And since that depends on the north velocity, that should be 0. Okay, so it should only be moving along the latitude. Okay, fine. So then r dot is actually 0 as well. I mean, obviously, so Coriolis force was 0. Alpha naught is 0 anyway. So that whole thing is gone. And then the other stuff, so the other acceleration part, which was, well, it was just omega dash omega naught, so 2 times of that plus, yeah, all that stuff. Omega naught squared r hat, this thing. This quantity should be 0 as well. And well, omega dash is actually, oh wait, it's not 0 all of the time. Sometimes it's not 0. Oh, huh. The north velocity, I mean, yeah, like the velocity along the meridian is 0. Normal to the meridian is not 0, so it's moving along one latitude circle. I don't know what that means. Okay, so that makes tangential force to be 0, so the t hat force to be 0. Then there's the Euler force, which is already 0. Don't have to worry about that. And then it's just this quantity that you have to worry about. So you want to make that 0. So then your omega dash should just be negative omega naught upon 2. Right. Once we have this, then it will be 0. Exactly. Right. So since the Earth is going from west to east, yeah, your train that should be moving towards west with an angular velocity of omega naught upon 2 times the radius of Earth, right? If it actually, no, it's just supposed to be smaller, or what I'm doing, just smaller. So whatever latitude it has, that cosine of that thing, that's capital R, yeah, that's our small r value. So this is how it should be moving, and it should be moving completely in the west direction. Once it moves like that, this will happen, and that if that happens, this is gone. So it actually does not have any inertial forces. Crazy. Yeah, it really is crazy. Fine. So 117, now you understand that. Wait, what? Where did it go? Oh, it's not 117. Sorry. What was this? It was 116. Yeah. So just put that in here. This will be A. And for B, you just have this as the velocity. This is the direction, west. Now, time to calculate this thing. Omega naught is 7.3 to 10 power negative 5. At this point, I just remember the whole value by itself because we have used this so many times. Upon 2 into the radius of Earth. Oh god, that's not nice. Uh-oh. Oh god, it's not good. It's not good. It's not good. Oh, okay. Fine, just put it in there. We'll see what we get. Radius of Earth is just going to be 64 to 10 power 5. Okay, this somehow works. And then you got cosine phi. So phi is, what is phi? 60 degrees, right? So it's supposed to be cosine of 60 degrees, which is just 1 upon 2. So there we go. It's 1 upon 4 right there. So it's going to be 16. This is gone. 16 into 7.3. That's our answer. So what will that be? 73, 16 is supposed to be what, like 81 kind of wrong. 42, 42 and 1. 4, 3. Yes, then you got 0, 7, 3. So 8, 6, and then 1, 1. So 116.8. Yeah. So this is approximately 116.8 meter per second. Of course, SI units. Cool. Let's go to the next question. So 117, it didn't ask anything about inertial forces, right? Yes. It was just 116 that I asked about it. And yeah, that's all it is. So cool. So now we can move to the next section. Laws of conservation of energy, momentum, and angular momentum. In this video, I'll just read these laws, and then in the next video, I will start solving. Work and power G of the force F. Okay, so A is so like A is the work. What kind of notation is this? A for all things. Like why A of all things? Why not W? Oh yeah, they already used W for acceleration. This whole book uses some really bad notation. Whatever. Work is integration of F dr. F is the force dr. I mean, like these are vectors, of course. So the dot product between them, which is the okay. So like the tangential force times the small element along the path. Power is force times velocity. At one point in time, I used to doubt if this is correct for every kind of motion. Actually, it is correct. I shouldn't have doubted this. So it's pretty easy. I mean, like dA is just f vector dot dr vector, and then divided by dt. So f vector dot dr upon dt. So f vector dot velocity vector. Exactly. I mean, from the definition itself, this actually, yeah, it works. So no, it will always work. And I was childish back then. Okay, the increment of the kinetic energy of a particle. So why are they using this kind of notation? T2. They could have used K. They could have used KE. What is this? T of all things. Okay, so T2 minus T1 is A. Wow. Okay, that's just like from the work energy theorem. Whatever work done by all forces are on this body, that will just raise this guy's kinetic energy. Which I mean is not that hard to prove. It's basically just this thing. V squared is equal to U squared plus 2AS. And from that, all you have to say is just, well, half mv squared minus half mu squared is equal to, well, mass times acceleration times displacement. Actually, it should be more like integration. So integration of a vector dot ds vector. So then it will just be mass times acceleration is force. So it's like integration of force vector dot ds vector, which is exactly what work is. So work energy theorem is actually correct all of the time for, I mean, at least it's correct for particles, right? I mean, particles moving under, normal kind of forces, not doing anything crazy like nuclear reactions. So yeah, you get the idea. So this is good. And then what we have, work performed by the forces of a field is equal to the decrease of potential. I mean, that is the way we define potential energy. Relationship between, where it go? Forces of a field and the potential energy of a particle is, so F is equal to negative gradient of U. Yes, that is from the definition itself. It's not even a formula. Okay, increment of the total mechanical energy of a particle is given in a given potential field. So A external, fine. Yes, like total mechanical energy change. This is very obvious, because all the G is saying is that E2 minus E1 is equal to whatever the change in kinetic energies. So why are they using E2 minus E1 though? I'll just use work 2. Wait, what? E2 minus E1. What does it mean? Total mechanical energy of a particle in given. Oh, so this is the external work done. Fine, 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 fine. Then they are just talking about, okay, the kinetic energy 2 minus kinetic energy 1, and then potential energy 2 minus potential energy 1 is equal to the work done externally. Okay, which is basically saying like K2 minus K1, which is our delta K basically, is equal to negative delta U plus work done external. Now there was something about negative delta U, I think. Yeah. Right. Work done by the forces of a field. So a considered field. It's just is equal to decrease of potential energy. So yeah, like U1 minus U2, that's the work done by the field on this thing. What do we call it? On the particle, right? Yeah, so that like just increases the kinetic energy, of course. Now over here you just have delta. Okay, this is wrong. How can that be correct? I mean, over here what should be happening is that U1 should be bigger so that the work is positive. It has to have a negative. They wrote an incorrect equation. Right, I mean, how can this be? Decreasing potential energy, right? So it's supposed to be from higher to lower, your work done on the particle is more. So actually it should be negative, right? So the work done W is just negative of U2 minus U1. Oh yeah, actually, sorry, this is correct. That is in fact negative of U2 minus U1. I really thought it was above. Okay, yes, this is correct, sorry. So yeah, like negative delta uses negative of U2 minus U1, which is just U1 minus U2, which is the work done by the field. So work done by the field and plus work done external. Of course, that is the work done on this particle using all of the forces, right? And that's why delta K, which is from the work energy theorem. So, I mean, it's really crazy why we use this. I mean, potential for concept. I know it simplifies calculation a lot. Yes, but even without using it, the physics still runs smoothly. So there's no necessity of defining this new thing called potential and saying it stores energy or whatever. Yeah, yeah, but it really, I mean, once you get to things like electrodynamics, it becomes essential. Yes, but even without it, what's the problem? I mean, physics still works. Just it's more inconvenient to write it. Anyway, I mean, the way it's taught is that uh, this this potential energy is actually an existing energy that stores. I mean, that is stored or something. No, that's not the case. The only energy that is real that can be, I know, like calculated without a reference to a zero mark, right? In the space frame, that is at least in one frame. So without defining zero mark, it can still be calculated, right? There's only one such energy, kinetic energy. Yes, kinetic energy is the only such energy. So I always like to think about kinetic energy whenever doing, work energy theorem. But yeah, mechanical energy itself is also good because this works. Okay, and then they are saying E is T plus U, which is the total mechanical energy. Okay, where T I think represents the kinetic energy and U is the potential energy. Okay, then they are saying increment of the total mechanical energy of the system is E2 minus E1. So mechanical energy at 2 minus mechanical energy at 1 is equal to A external plus A non-conservative. What is this INT mean? Huh? INT? I don't know what that means. Whatever. And then U is the inherent potential energy of the system. Whatever. Law of momentum variation of a system. Isn't that just the definition of force? What are they talking about? Why are they giving it right now? It should have been a laws of motion. equation of motion of the system center of inertia. So yeah, I mean, this is actually very obvious, right? So F is equal to mass times acceleration of the center of I mean the center of mass of the whole rigid body or whatever system, right? That's just the sum of all the external forces applied on a system. Makes sense? Yeah. I mean, do you need a derivation for that really? Come on, I'll give it a derivation. So you know that the center of mass is defined like this, that XCOM, which is a vector basically. The position of the center of mass, that thing is just mass, sorry, it's just summation of mi xi vector upon summation of mi, right? And then when you integrate this thing, and summation of mi is basically what they're calling small m. Sorry, and when you differentiate this thing, just get velocity vector of com. It's just a summation of, yeah, like this, all of, like, okay, cool. Times the velocity vector of each of these upon mass. So then acceleration vector of com is just the same thing, like mi ai vector upon m. Now the good thing is that, so mi ai vector is just the result of the forces, all of the forces put on a particular particle. So just summation of all of that combined. Now, some of these forces will be internal forces. So those are applied by some other particle on some particle, right? Those interactions, well, they will have an action reaction pair kind of, I mean, thing. So they will cancel each other out when we'll sum this up. So it really is just the external forces. Yeah, that's why MACOM is just the all external forces combined. Why am I doing this? So this is pretty obvious. Kinetic energy of the system. So kinetic energy is equal to, what is this? Kinetic energy system of the center of inertia. Oh yeah, it's just, okay, I understand this. Center of inertia is center of mass, and yeah, this is correct actually. But I can even prove this if you want. Should I? Let's just prove it, because why not? If I have free time for this video, I'll prove this. So once again, starting from the definition, you can just say, okay, velocity of center of mass, that vector, or okay, just say m velocity center of mass, that is equal to, or in fact, I'll just go for velocity of center of mass, whatever. This will just be equal to what was the thinking? Yeah, like summation of the MIVI thing upon M total, right? Now, what we are looking for is half summation of MIVI squared upon MI, but we know that we can write VI squared as, well, V dash I vector plus velocity of center of mass, which I will just call VC. They are also calling the same thing. That vector squared, right? So this just tells us, and yeah, right. So V dash I is basically just the velocity relative to the center of mass. Okay. So squaring is just get Vi dash squared plus Vc squared plus yeah, what was I doing? Okay, 2 Vi dash times Vc dash, sorry, Vc, yeah, right. Now the good thing is that I'm like, this m is just summation of mi basically. We can send this over here, summation of mi times all of that, and then we can do this thing, summation of mi into v vector, so I vector minus vco m vector, so vc basically, that is equal to 0. But what's this thing? Just v dash, right? So vi dash, basically it's saying like summation of vi dash vector, right? That times mi, of course, that's equal to 0. Now let's think about it. We just want this. Wait, why am I dividing by mi over? That should not happen, sorry. Then you can just replace this vi vector square by this thing, right? So summation of this thing, of course, that times mi, yeah, let this be half summation of mi vi dash square, which is basically the kinetic energy in the frame of reference of this guy, of the center of mass. Yes. Okay. Plus um, this thing. So just do mi vc square and then summation of that thing. Well, that's just half of the total mass times vc square, because you can take that vc square out, right? And then finally you have this thing. So over here you can take that vc vector out, all right, and it's dot product, so you can still take it out, no problem. It just becomes vc vector, and then half and 2 gets cancelled, whatever. It's got summation of mi, it's supposed to dash, sorry, mi vi dash vector. But wait a second, what's this thing? What's that thing, huh? It's supposed to be dash over there, sorry. So we know this thing is just 0, so you can get rid of all of this. So it's just the kinetic energy in the frame of reference of the center of mass, and then you got this extra term, which is the kinetic energy of the center of mass in the space frame. Should make sense, I guess. Yeah, and then you can write similar kind of things for, I don't know, like inertia and all of these different things, whatever. Angular momentum. Yes, so angular momentum also behaves somewhat similarly, right? It's the angular momentum of the center of mass and then angular momentum of the whole body with respect to center of mass in a particular coordinate, in some particular coordinates. So both of these frames have the same kind of coordinate axis, just the origins are different. That's all it is, all right? So the coordinates are not rotating, coordinate axes are not rotating just with respect to each other. That's what I'm saying. So yeah. Okay, then you have equations of dynamics of a body with variable mass. mdv upon dt is equal to f plus d upon dt times u. Oh, okay, yeah, it just comes from the definition of momentum. And yes, but use the velocity of the separated gained substance related to the body constraint. Oh, huh. Wait a second. What? Separated substance? Okay, so it's a body with variable mass, but shouldn't it just be f is equal to m? Oh, okay, okay. I'm understanding what is going on. U is the velocity of the separated substance related to the body constraint. So U is like negative of the, I think it's not negative v vector. That can't be. No, that can't be. But you really have like force is just mdv upon dt minus d upon dt times u. But that's not how it should be. Okay, it's just dp vector upon dt, which is like d upon dt times v vector plus m times acceleration vector. That should be it. What is this equation? I don't know. Velocity of separated substance related to the body constraint. Okay, this is getting bad. We'll leave this. Okay. Law of angular momentum, variation of a system. M is the angular momentum of the system, and is the total moment of what external forces. N, they are not using torque, they are using N, and they are using T for kind. What is this notation? It's just really stupid. And M is the angular momentum, not L. Why? Everyone in the world uses L, and you're using M and N for some reason. Okay, angular momentum of a system. And moreover, they didn't even define what angular momentum is. So yeah, I have no idea why they gave us all of this when it was not full of definitions, just full of these weird things. These angular momentum of the system, that's the angular momentum of the center of mass. Yeah, plus the angular momentum of the body as seen by the center of mass. Okay, So that's basically like the inertia, and P is the momentum of the system. Oh wait, what? R is the, oh yeah, of course. So M is the angular momentum in the center, in the system of the center of inertia, so center of mass basically, right? So the angular momentum of the body as seen by the center of mass, and plus this quantity in bracket is just the angular momentum of the center of mass as seen in the space frame. So MBR, right? Then you have questions. So I'll do that later. That's it for this video. See you guys in the next video. Bye.